I will welcome people. I am pleased that we have Gard taking us on this version of Gauge Theory Virtual. He's going to talk to us about calculating equivariant instanton floor theory for some space forms. So I'll let him take it away.
Thank you. Yeah, so first, I would like to thank the organizers for giving me this opportunity to speak. So yeah, the title is Calculations of Equivariant Instanton Floor Groups for Binary Polyhedral Spaces. So I'll just give I prepared a little bit here. The basic outline here. So, well, first I will spend a little time to say what I will be calculating, which are, so give some background on equivariant and instanton Floor homology in the sense of Mike Miller-Eismeyer. So this will involve some formal aspects, overview of the construction, and then I will talk a little bit about a simplified model for that can calculate these groups. I will come back to this. And after this, these preliminaries, I will talk about some description of these complexes for what I call Y gamma bar here, which is notation for the binary polyhedral spaces that I will introduce later, and talk about mention some main ideas of the proof, like how can we actually calculate these Floor groups in this situation. And depending a little bit on the time, I will discuss some of the algebra involved in passing from this complex here to the actual Floor groups. So I'll make this a bit more clear after having gone through the overview or the equivariant Floor theory. So the basic setup I will consider is Y to be a rational homology 3-sphere and equipped with the trivial SU2 bundle. So I will throughout work with a fixed principal ideal domain of coefficients for the Floor groups. And then the equivariant instanton Floor groups comes in 3 flavors. We have the I plus, we have the I minus, and the I infinity or Tate equivariant instanton Floor homology. So just the formal properties. Well, they are graded over C mod 8, and they carry module structure over the cohomology of the classifying space of SO3, and they fit together in an exact triangle, like this. So these are the degrees of the maps involved. So how do we construct these groups? Well, so here is a broad overview or the whole construction. So initially we consider a framed configuration space of connections in the bundle E. This carries an action of SO3, and the Chern-Simons functional is SO3 invariant. So then we get a package of critical orbits and instanton moduli spaces. I will just write equivariant Morse dot theory, and this set of data is transformed into first of all, a big complex CI tilde of YER, equipped with an action of the chains of SO3. So I will elaborate further on this part shortly. So call this M and this differential graded algebra A. So from here, the rest of the construction is purely algebraic or homological algebra. So we have three functors, C plus A, C minus A, and C infinity A for a DG algebra A and a DG module M. So it's desirable here to introduce a completion to get new functors C hat plus A, C hat minus A, and C hat infinity A. So this is the algebraic analog of sort of the Borel construction in topological spaces. So it's equivariant homology. So and finally, we can take homology to obtain the equivariant instant Floer groups I plus, I minus, and I infinity. So I will now go a little back and just be a little more precise about this part of the construction. So we go back to our bundle E or Y, we fix a base point, and we form the space of frame connections by taking the usual space of connections and joining a framing coordinate. So the gauge group GE acts in this situation freely, so diagonally, and we get a quotient space, frame configuration space, which is an honest Hilbert manifold in appropriate Sobolev completions. And the action of SU2 on the fiber here descends to a residual SO3 action on the configuration space. So then we just extend the Chern-Simons functional by ignoring the framing, and it becomes SO3 invariant. So I will let throughout C denote a set of critical orbits. So this is still the set of flat connections modulo gauge, but I think about it that we also remember the stabilizer. So as is usual, we get different orbit types depending on the stabilizer. So the possible orbit types are a full irreducible orbit, and we call these irreducibles, or we have a stabilizer SO2, which yields an what I call an reducible orbit, or finally a fully reducible orbit, where the stabilizer is all of SO3. So we also say abelian or central in terms of the flat connection interpretation. So generally, one has to introduce a perturbation to make all of this, to make the flat connections or the critical orbits non-degenerate, and eventually have the moduli spaces of instantons or flow lines in this situation cut out transversely. But I will ignore this point, well, in particular because for the binary polyhedral spaces, which is the situation of primary interest, this is not necessary. So from there, we get a package of moduli spaces or of geometric data. So for each pair of critical orbits and a choice of relative homotopy class, going from the critical orbit alpha to the critical orbit beta in the configuration space, so we get a well-defined moduli problem of the cylinder. And this leads to an instanton moduli space. So I'll just say loosely that we are considering AST connections, or the cylinders, with the framing that approach alpha at -infinity and beta at +infinity. And the instantons should belong, the corresponding path in the configuration space should belong to the homology class set. So this M set bar notation refers to also translation reduction and then the compactification, but I won't be too precise about that. So index theory gives a well-defined number, GR set of alpha beta, for each piece of data. And if this moduli space is non-empty, its dimension is determined by this grading, by the GR set alpha beta plus the dimension of the orbit alpha -1. So this is independent of the homotopy class set modulo 8. So we get a well-defined relative grading in C mod 8. So finally, in the situation of a trivial bundle, I take the trivial product connection as a reference point and define an absolute grading in C mod 8 by J of alpha is equal to GR alpha to theta. So I will now tell you how you can define the simplified model for the Fuller complex. So this is in simplified model for this CI tilde that I introduced briefly earlier. So as a graded module, the DCI YR ST is just given by sums of the homologies of the regular homologies of the critical orbits. So I will give an example shortly that makes this a little clearer. And the differential in the complex decomposes according to the bi-grading here, where the bi-degree of the rth component is -r, r -1. And these components of the differential is defined via these diagrams and using the compactified moduli spaces. So all the components of the differential has a concrete description in terms of counting flow lines or counting instantons with prescribed holonomy. So let me give an example of what this looks like. So, yeah, I should mention here that so the actual Donaldson model is the totalization of this bi-graded module defined here. Okay. So here's an example. So suppose the critical set consists of 3 elements, theta, the product connection, and 1 irreducible, so fully reducible, irreducible, and reducible. And that we have grading such that theta is in degree 0, lambda in degree 0, and alpha in degree 4. So the irreducible in degree 4 contributes two copies of R along this in degree 4. The reducible theta contributes one copy here, and this repeats periodically in both directions. And reducible lambda contributes these two copies of R. So when we take the totalization, we take the sum along the rows in this fashion. So it's important that we regard this. So this is just a graded module. So in this case, when everything else is 0, the only potentially non-trivial differential is this fourth component, D4. So the other differentials so D1 would go 1 across, D2 would go 2 across and 1 up, and D3 would go 3 across and 1 and 2 up. So due to the grading here, the only potentially non-trivial component is this fourth one. So it's important that we regard this complex here as a module over the homology of SO3. So this is an exterior algebra of a single generator U in degree 3. And well, the action is on the columns and only on the irreducible ones. So in this example, since we only have one irreducible alpha, the only action is U taking a generator here up to the generator here. Now, finally, I should mention that so we are actually we can actually reach the equivariant Floer group through these algebraic constructions later. So we can use this DCI with the action of lambda RU to calculate equivariant Floer groups. Okay, so this is basically what I want to say about the equivariant Instanton, so the geometric part of the equivariant Instanton Floer homology. So now I'll return or start talking about the spaces I'm interested in, so the binary polyhedral spaces. Yeah, so the binary polyhedral spaces are the orbit spaces S3 mod gamma for a finite subgroup gamma of SU2 acting on the 3-sphere in C2 through the inclusion in SU2. So the finite subgroups of SU2 are classified. It's a classical result that we have cyclic groups of all orders. We have the binary dihedral groups Dn star. So these are the pullbacks of the dihedral groups in SO3. And finally, we have 3 exceptional ones. We have the binary tetrahedral, octahedral, and icosahedral group. So we can note here that these YCL are just the simple length spaces, and Y star is the Poincare sphere. So I will sort of give the description of these Donaldson models for Y gamma bar. It's convenient to reverse the orientation to get the nicest description. But having the description of one of them gives also the description of the other, so we can note that DCI of Y gamma with the standard orientation is isomorphic to the dual complex. So it's easy to get the standard orientation from this one as well. So I let C be the set of critical orbits as usual, and then associated with each subgroup gamma, there is a graph called S gamma. It turns out to be a connected tree in all cases, and the vertex set is precisely the set of flat connections or critical orbit C. So I will give you the construction at a later point, but first, so just to give you a sense of what these might look like, here is the example for I star, O star, and T star. So for I star, we have the trivial connection and two irreducible alpha and beta. And for O star, we have two irreducibles and one fully reducible. And for T star, we have one irreducible and one reducible. So what is the key theorem then? This is due to Fronheimer, unpublished. It's stated in a paper of Austin from '95, where Austin also considers calculations of binary polyhedral spaces, but for a different equivariant Instanton Floer theory developed by Austin and Brown in '95 or '96. So the basic importance of this graph is gamma is that if alpha and beta are adjacent vertices, then we can identify the moduli space of instantons, essentially. So basically, if we take set to be so we're interested here in the moduli space of minimal dimension. So that's how I sort of specify the homotopy class here. But in that case, the fiber over a point by E minus is given by another space form S3 mod gamma prime for some other finite subgroup gamma prime in SU2. Furthermore, we can also show that if alpha and beta are not adjacent in this graph, then the moduli space, the minimal dimensional moduli space, is empty. Now, if beta here is irreducible, so copy of SO3, then the differential in the Floer complex or in the Donaldson model is given by the degree of the restriction of E plus to the fiber. And Austin also gives a formula for the degree of this map. And this is a fairly simple procedure to find these, to determine these degrees. But yeah, I won't introduce all the theory necessary to give you the explicit formula. But essentially, this theorem allows us to describe the Donaldson model completely. So first, I should mention that, well, when the fiber has dimension 3, then the relative grading melon alpha and beta must be 4. So this gives the corollary that the relative grading for y gamma bar is given by 4 times the length of the minimal path connecting the trivial connection to alpha in this graph as gamma. So for the binary octahedral group here, we have this graph as O star, and then we can easily read off the grading. So the first one is degree 0, 4, 0, 4. And this gives DCI in this shape. So theta and beta contribute these two, and alpha and eta contributes these. And this repeats periodically. And so I can also, using Austin's degree result, we can also find that the differential here is given by, so basically the fully reducible eta gives 1 in the differential, and the action between the irreducibles is multiplication by 3. And the same happens for the other differential. So this is the description of the Donaldson model for y O star. Yeah, so this is the thing seen here in this example, that the only non-trivial part of the differential are these. D4 is a general phenomenon. So as mentioned, the implication is that the grading is divisible by 4 in all cases, and this means that the differential delta is D4. And well, this is basically what I mentioned earlier concerning the action of the differential. So my main result in this direction is then to give these graphs as gamma for all subgroups, and I can show you in this example. So it's we attach labels to the edges to record the differentials. So we put a 1 here for the action between theta and alpha and eta and beta, and then I record the action between the reducibles by such a double symbol. And this we can do in all cases to get the graph that completely describes the Donaldson model. Yeah, so this is the main first result. So the second main result is to actually pass from this complex to the equivariant Floer groups. And this is a rather big exercise in homological algebra and spectral sequence calculations that I will talk a little bit about towards the end. But I want to say something about the proof of this this main theorem here of Kronheimer and Alston, which is sort of the interesting geometric part in this investigation. So rather generally, we can say that when we do, well, SU2 gauge theory over the cylinder R cross S3 mod gamma, this corresponds very precisely to gamma equivariant gauge theory over S4 with a suspended gamma action. So as mentioned earlier, these the moduli theory over the cylinder depends, well, we get one moduli problem for each so-called adapted bundle, which involves having an SU2 bundle with prescribed flat structures along the ends, in addition to this relative homotopy class. So this data essentially describes what I mean by an adapted bundle. And this corresponds very precisely to gamma equivariant SU2 bundles over the force field. So the adapted bundle with flat limits alpha minus and alpha beta. Yeah, so let me just say that when gamma acts on S4 with the suspended action, then we have fixed points. The action is free away from the fixed points, which consist of the N and S, which I call the north and south pole. So for a gamma equivariant bundle, we get gamma representations over the fixed points, which I brought here as En and Es. And these are corresponds precisely to the holonomy representations of the flat connections. While this relative homotopy class can also, in a sense, be identified with the second Chern number of the corresponding non-equivariant bundle. So we can set up this correspondence between adapted bundles and equivariant SU2 bundles. And furthermore, this extends to a matching of the instantons on the adapted bundle with the gamma equivariant instantons modulo gamma equivariant or gamma invariant gauge transformations in the equivariant bundle. So by this I mean, well, here I have a framing involved too, but at least naively, we take the space of connections and take the subset of invariant connections and divide out by the group of gamma invariant gauge transformations and adjoin framing coordinates. So then this can be made rather precise. And having transformed the problem onto an equivariant problem on the fourth sphere, we have then an equivariant version of the ADHM correspondence describing the framed moduli space of instantons on this equivariant bundle, where the framing is at the north pole. So this is a property of the equivariant ADHM correspondence in this form, and this framing at infinity corresponds to, or at the north pole corresponds to, framing at infinity on the cylinder, in a sense. So that's why we get the description of the fiber of the endpoint map. So yeah, I should rather. Yeah, so solving these equivariant ADHM equations leads to the theorem. Now this is a rather involved thing, and it is intimately related to Kronheimer's 89 paper on Ale spaces as hyperkähler quotients. So before I say something about the algebraic part, I will just give you the definition of these graphs as gamma, although it might seem a little unmotivated. So first of all, we have the McKay correspondence between the finite subgroups of SU2 and the extended Dynkin diagrams of type ADE tilde. So here's the precise correspondence. Cyclic groups corresponds to the ones of type AL. The binary dihedral corresponds to dm+2. And T star, O star, and I star corresponds to the exceptional ones, E6, E7, and E8. Yeah, so here are the graphs. So just to briefly recall how this correspondence is set up. So we take a full set of representatives for the irreducible complex representations of gamma, call them R0 to Rn. Let Q denote the canonical representation corresponding to the inclusion of gamma into SU2. And then define a matrix A by decomposing Ri tensor Q into isotypical components. So Aij's are the coefficients. And these turn out to be in 0, 1 in all cases. So the corresponding McKay graph or extended Dynkin diagram is then defined to be the graph with adjacency matrix A. So in particular, so each vertex here is associated to an irreducible complex representation of the corresponding group. Now, mapping an irreducible to its dual gives rise to a graph involution, iota, and the vertex set of the quotient graph can be, by some elementary representation theory, be identified with irreducible quaternionic representation of gamma. Now, our critical orbits, so the irreducible SU2 representations, corresponds precisely to the reducible quaternionic representations. So we can regard C as a subset of the vertices of this quotient graph, this one. So I will describe how we, let me just do an example to say where we go from there. So this is for T star. Here is the Dünking graph, where I have denoted the flat connections in here. So we have the trivial connection theta, or rather complex representation. Alpha is an irreducible two-dimensional representation. And we also have a one-dimensional complex representation rho on this side, and this is the dual. So the involution fixes these ones and sends these across. So the quotient graph is looking like this. And the reducible flat connection is seen then here as the direct sum of rho and its dual. So now the S gamma is obtained by essentially replacing, so just omitting the vertices that are not one-dimensional or correspond to flat connections, a little loosely. But so we replace these three edges there by a single path to get this graph. And this works nicely in all the other cases as well. Okay. So I think I'll go over to the algebraic part now in the end. So the basic point of the first part was that we get all these complexes in DCI. And, well, we are interested in getting the actual equivariant Slur groups. Okay. So we are considering the pair consisting of A, this exterior algebra on a single generator, U, and the Donaldson model for some rational homology free sphere for that sake. So then we have these functors C plus A and C minus A from the category differential graded modules over right modules over A to left differential graded modules over C minus AR. Now this turns out to just be R view with trivial differential. So in particular H, but when in partial homology, we get R view as well, where U has degree minus 4. So I can, let me say what essentially C plus A is. I haven't, so C plus A of M. So this is special to the case when A is an exterior algebra. But then we can write this as the total complex of M tensor R V, where this part here is a polynomial algebra on a generator, the of degree 4. So the elements here, x in C plus an, and this can be written as a sum x n minus 4p t greater than 0 tensor v to the p. And the differential here, I haven't checked the signs completely in this description, but so I will just write that the differential is then the internal differential on this component in M, tensor Vp, plus or minus the action of Q, and we decrease the index of the placeholder by 1. Yeah, and I should mention that the action of R of U C plus AM is just by contracting the in the V. So U dot, let's say, x tensor Vp is equal to x tensor Vp minus 1. So for C minus, we get essentially the same thing. So this time I want to use we get a total complex. This time we have to take a product of M tensor R of U with U equals minus 4. So this time the elements are like power series, like this. So these DCI yeah, let me just write DCIY. They come equipped with a filtration. So when I described it like a double complex earlier, this was just an example. Comes equipped with the filtration by columns here. So C plus minus A are exact. So there's an induced filtration. FP. Yeah, so I denote the filtration by FP DCI for P instant. C plus minus A of M is equal to C plus minus A of FPM. So what do I want with this filtration? Well, this is because I want to complete with respect to the filtration. So that's the C hat A of M is the completion of, I should say, C plus minus here with respect to this filtration. So luckily in this very basic situation, not too much is happening, or rather, so I described C plus here as the totalization of M tensor R of B. So in the completion, I just have to change this plus with a product, and conversely, in the minus, I have to replace this product with a direct sum. So this is special to the situation with an exterior algebra. But C hat plus A of M is the product totalization of M tensor R of B, and C minus hat of M is totalization with respect to the direct sum. So the good thing with these totalizations is that the filtration induces a spectral sequence, which then converges. So we have spectral sequences so the general form is C hat A plus Fs M, or Fs minus 1 and S plus T. Oh, I should pass to homology here. So H plus minus A converging to H plus minus A of M. So for M equals DCI, this here is my I plus minus of Y ER. So the reason one introduces the completion is to ensure that these types of spectral sequences, called the index spectral sequence, converge to the correct target. So, and I should also mention that I have taken a little bit of a different approach to the completion than Mike Eismeyer's original approach here. So when we go back to DCI, so the original HT of alpha. So what happens when we apply this spectral sequence in this situation is that the E1 page describes the equivariant homology of precisely the orbits. So in this situation, we get E1 ST equals the direct sum alpha in C J alpha. I'm going to S H plus A of the orbit alpha. So this is the, I can say, plus minus converging to I plus minus of Y ER. So we have orbit calculations. So H plus A. Yeah, so I should mention that this means H plus minus A of the homology of alpha. So H plus, we get RB alpha with B alpha equals 4 for alpha fully reducible, R of what I call W alpha equals 2 for alpha reducible, and just a single copy of R in degree 0 for alpha irreducible. So the reason I wanted to say this is that now I can actually state calculational result. So the key point here is that these 4-bit calculations, these are all concentrated in even degrees. So G alpha is in degree 0, W alpha always in even degrees, and E alpha always in powers of 4. So for y gamma bar, we know that the grading is congruent to 0 mod 4 for all alpha in C. This implies that also the differentials in the spectral sequence has by degree minus r minus 1. So they must go from an even total degree to an odd total degree. So for degree reasons, E1 equals infinity for this spectral sequence. So then I can at least additively state a uniform calculation for I plus y gamma. So the theorem, so there is a little bit left in actually obtaining, we have to resolve some extension problems to get the action of R of U in this situation. But I plus y gamma bar with coefficients in R is, well, we basically just get, since there are no differentials in the spectral sequence, everything survives to the actual third group. So for alpha in irreducible, we get a copy of R dot G alpha for some generator, and we have to twist this by the grading, and for each alpha and each reducible, let's call it lambda, we get the copy of this the lambda twisted by the grading, and finally for each fully reducible, we get a copy of the polynomial algebra, the eta twisted by the grading. And so from here, I have to do an operation I call product, comma 8. So if M is an RU module, I define product 8 to be equal to the product, or S in set, M of 8S. So this forces everything to be mod 8 periodic. And this is exactly it. So I can say that this thing in here is the infinity of the spectral sequence, and this happens when we resolve the extension problems. So what remains is to actually describe the action of R of U. So I can, yeah. I won't go into that. So I can say that for the I minus, we get the spectral sequence. So the index spectral sequence has many differentials. Many is not really accurate for T star for these exceptional ones, but for the binary dihedral groups, there are quite a lot of differentials. But we can check that it eventually stops. So E R0 equals E infinity for some finite R. So I think I will stop there. It's not really very pretty to spell out all these actual calculations. It depends a lot on actually finding all of that connections, and then we get rather big modules. But the point is that it's possible to get explicit calculations in all cases. So I can just finally mention that I posted the paper with all the calculations on the archive for a couple of weeks back. So maybe I can link it if anyone's interested. But okay, thank you.
Okay. Well, thanks, Gard. Are there questions?
So can you say, I don't know, there must be some, at this point, standard conjectures about how this equivariant instanton theory should be relating to, I don't know, either Seiberg-Witten type Floer homologies or maybe even Hegardt-Floer homologies. Are these, is this, I mean, because these are, of course, are all L spaces that you're in the both Hegardt-Floer and Seiberg-Witten. Is this somehow, is this consistent with all those whatever conjectures there are? I don't know.
I don't know, but I'm not so familiar with the other types, the Seiberg-Witten and Hegardt-Floer. But yeah, so I can't really say anything useful there.
I mean, it may be in some sense a question for the audience. I don't know whether anybody can say.
Nobody's saying anything. May I ask, maybe you could explain the difference between your completion and Miller-Eismeyer's?
Yes. So so what I do, I complete directly with respect to the filtration on the Floer complex, while Mike is making some completion directly. So underlying these C plus, C minus, and C infinity is the bar construction of algebraic topology. So his C hat A of M would then be the completion. So this is C plus A of M. So if you're familiar with the bar construction, so this is the completion of B of M A R with respect to the internal degree in the bar construction. So that is Q. So Yeah, and for the C hat minus A, Miller uses Miller-Eismeyer the finitely, what he calls the finitely supported co-bar construction, which amounts to, so this fin here, finite, means that we only take functionals that vanish for big P, where P is the simplicial degree in the bar construction. And so my slight issue with this, well, first of all, I can mention that the two completions agree for C minus and C plus. There's rather some little subtle issue in the case of the Tate version of instant Floer homology, where I'm not sure that this completion really does what it's supposed to.